Humans act and justify their behaviors using their past experiences and what they have learned from similar situations. Likewise, machine learning models leverage the most similar patterns from the training set in order to make predictions. Unlike previous extractive approaches for explainability, in our work entitled Towards Unifying the Explainability Evaluation Methods for Natural Language Processing, our goal is to justify a neural network's prediction using phrases from the training set, and we measure their influence on the prediction via a newly introduced contribution metric. The objectives of our research work are to preserve the performance of the explained model while generating multi-word expressions as explanations that are insightful and useful for machine learning experts and that allows them to detect whether a model is able or not to capture the semantic meaning of the text that is being classified. The task and the dataset that we have used are the binary classifications task for sentiment analysis using the IMDb movie review dataset. This allows us to perform automatic evaluation of the polarity of the explanations and to compare those to the prediction and to the goal truth label. In terms of the methodology, we are first using an unsupervised manner of extracting a dictionary of possible explanations using Rake, and the architecture consists of two main modules. Firstly, we have the classifier, for which we've chosen the BiLSTM architecture, and this is the model that is being explained, and the generator, which outputs a probability distribution over the dictionary of all possible explanations considered for the task. The model architecture's diagram depicts how the two models work together. Firstly, the instance under classification is passed through the BiLSTM model, outputting the first sentiment prediction. The BiLSTM representation is fed as input to the generator, which outputs an explanation, and the explanation, when concatenated with the original text, is passed again through the original model, outputting a second prediction. The difference between those two predictions is what we call the contribution metric, and it represents the added value of the explanations in the correct prediction. The value can be positive when the explanation brings information relevant to the correct prediction, and it can be negative when the explanation influences the model towards making the wrong prediction. For the quantitative analysis, we have analyzed the consistency of the polarity of the explanations with the prediction and with the goal truth in Table 1. And with this analysis, we aim to assess what is the performance increase in Table 2 when the generator is being used, and what are the contribution ranges of the generated explanations in Table 3. We couple those insights with the qualitative analysis, which consists of human evaluation, in an extensive evaluation of the approach, which allowed us to draw the following conclusions. The novel unsupervised framework for generated explanations for deep learning-based text classifiers preserves the performance of the explained model, and the novel contribution metric assesses both the impact of the added explanations to the text that is being classified and its faithfulness to the original model. Reporting both quantitative and qualitative analysis allowed us to perform both model interpretability and semantic model comparison. Please see the full paper for more details. We discussed both the qualitative results and the quantitative ones and derived meaning out of them, along with other useful statistical information, such as the frequency of the words or expressions in the training set. Thank you for your interest and for your time in our research.